Hi, everyone. My name is Mela Coffey, and I'm excited to present to you some work that was recently accepted at this year's ICRA. It's called Heterogeneous Coverage and Multi-Resource Allocation in Supply-Constrained Teams. And to kind of break this title down a little bit, I'd like to start out with an example. So here we're considering a team of firefighting robots. Each robot is equipped with different resources like water, flame retardant, or both. And they also have different capacities for the amount of water or flame retardant that they can carry. So we have this heterogeneous team here, and the team is tasked with supplying these resources, so the water, flame retardant, to different peak fire locations, and these are considered the demand. So the question becomes, how do we deploy robots with different resources to meet that demand? So our goal here is to develop a control policy for multi-resource deployment capable of continuous and distributed implementations. And we propose a Voronoi-based coverage control approach. So if you're unfamiliar with Voronoi-based coverage control, I'll briefly discuss it here. First, we have the robot positions. These are the blue circles in this figure. And given those positions, we compute the Voronoi partition. So each robot has its own cell, and all of the points in that cell are closest to that robot. Then given some density function, so here we have a density function phi equals 1, we compute the centroid of that cell. And then the robots move to their centroids, and we repeat from the first step. So this whole thing is called Lloyd's algorithm, and it's used to get the robots to essentially cover a space. So essentially all of the robots are responsible for covering the points in their cell. So the benefits of using Voronoi-based methods is that we can have a distributed network in the sense that each robot's behavior depends on the location of its neighbors, and the topology is not fixed. The algorithm is also adaptive in that it can adjust to changes in the environment, in the network, and the topology, and the sensing task. And the robots can also be asynchronous so that they can evolve at different speeds. So there has been some prior work related to coverage and heterogeneous teams. So the first is heterogeneous sensing using weighted Voronoi diagrams. So here the size of a robot cell actually increases with increased weights. In our firefighting example, this would be equivalent to increasing the size of a robot cell if they can carry more resources. But this only accounts for a single resource type and doesn't really put the robots where they need to be. In other studies, they do account for multiple resource types and assign them to different locations based on whether the robot has that type. So this would be equivalent to assigning robots with water or fire retardant or both to different demand locations, but these approaches don't account for how many resources each robot has. So our work aims to bridge that gap here. So we propose a coverage control policy for deploying heterogeneous team with supply constraints to multiple demand locations. And we provide analyses to prove minimization of the locational cost. And we also provide simulations and hardware in the loop experiments to demonstrate our performance. And now I'll get into the details of how we deploy our robots. So I'll walk through an example as I explain our approach. So here we're considering 8 robots shown in the bottom left here, and 3 demand locations denoted by the X's. In our firefighting example, these X's can be like the center of a major fire. Next to each robot is the number of resources of type K that the robot carries. So for example, next to this robot here, we might require 8 gallons of water and no flame retardant. And next to each demand location is the number of resources of type K at that location. So this fire might require 50 gallons of water and 8 gallons of flame retardant. So once we know the supply and demand quantities, we can assign robots to partitions. So we create one Voronoi partition for each demand location, and then we assign all of the robots who can possibly serve that demand to that partition. So for example, the top partition shows the demand that requires only water, right? Because we require 5 gallons of water and no flame retardant. So all robots that carry any water will be assigned to this partition because they can potentially serve that demand. And then we get a cumulative partition that looks like this. So given that partition and the density function, we compute the centroid and the mass of each cell. So recall these formulations for the mass and the centroid related to the density, and we'll use the density to represent the demand. So when an area has a higher density, the demand will be higher in that area. And I'll define that later. Then we define the locational cost as the sum over all of the robots and all of the demand of the individual costs. So a higher demand or a lower performance will increase the cost, but a robot can lower that cost by going to the centroid corresponding to the higher demand. Then each robot computes its control input by solving this minimization problem at each point in time. And it was shown in these papers at the bottom that minimizing the cost is actually equivalent to minimizing the energy subject to some execution task. They propose to enforce this constraint using control barrier functions. So we can take the control barrier function to be the negative of the cost so that the CBF constraint essentially drives the cost to zero. Here we're minimizing the input or minimizing the energy subject to this CBF constraint, where alpha is an extended class K function, and then taking our cost function and allowing the robot's single integrator dynamics, we reformulate the problem to this kind of ugly formulation here. So now the question is, how does minimizing the cost deploy robots to demand? In other words, how do we define the density function such that as the robots meet the demand, the cost decreases? So now we'll get into defining the density function or the team performance. So first, we represent each demand location as a Gaussian distribution proportional to the number of resources it requires. Then we do the same thing for the resources that belong to those partitions, and we represent each robot in the partition as a Gaussian distribution, also proportional to the number of resources it has. And then we sum over all of these robots to represent the overall supply. And then we can define the entire team performance as the demand distribution divided by the supply distribution. So here we have the demand, we divide that by the supply here, and we get this overall density function. And we can kind of get this cumulative density function that looks like this on the left. And this is what you will see in the simulations and experiments. And now I'll get into our simulations and hardware in the loop experimental results. So this is the same example that we've been following so far. The robots are solving the minimization problem at each point in time to compute their output. And we see that the total cost decreases and is able to reach a local minimum. We also carried out simulations where we compare what we call a hidden capacity and a known capacity case. So the known capacity case is our proposed approach, and the hidden capacity case is basically a binary version of our approach. So the robots only know whether or not they have a resource type. We also see that the cost is much lower in our proposed approach here. We conducted these known and hidden capacity cases under two scenarios. We randomized team parameters and we also randomized demand parameters. So these box and whisker plots show the final cost over 50 trials. And in both scenarios, our proposed approach results in a lower cost. And finally, we conducted hardware in the loop experiments with our new limo robots. So here we're just showing one resource type with 2 demand locations and 5 robots. Here, the robot positions are known via motion capture, and steering commands are sent wirelessly from a central computer. And I'm just going to pause it at the end here so we can kind of compare. So in the top, we have a demand of 15 in the bottom left and a demand of 30 in the top right. In the bottom scenario, we have the same thing, but the demand is swapped. So we have 30 in the bottom left and 15 in the top right. And we see that this middle robot ends up turning around to go help out on the other side where the demand is higher. So in this work, we propose a coverage control approach to resource allocation, where we consider multiple resource types and quantities. We utilize Voronoi-based coverage control to minimize the locational cost, which allows for distributed and decentralized implementations. And in the future, and what I'm working on now is implementing depletion dynamics, where the domain depletes as the robots supply the resources, and observe how the robots behave not only when new demand is injected into the system, but also when the demand moves. And then we want to figure out how to allow the robots to replenish their resources, for example, at a replenishing station or a recharging station when the robot resources are completely depleted. So thank you for listening, and feel free to contact me if you have any questions.